So yesterday I was giving the construction of the holonomy of a leaf. Okay, so essentially it was a representation from the fundamental group of the leaf L. We can fix a point, and I said that if you change the point, they are these homomorphisms are isomorphic onto to the diffu of sigma 0 p0, okay, where to each element in p1 of L gamma we associate gamma phi of gamma, where I recall that here this was representing the group of germs of the diffeomorphisms of sigma 0 that leaves p0 fixed. Okay, and I recall that is the set of germs. Okay, so if I have a leaf, I can have here different singular points. I can fix a point p0. I can take here paths generating our fundamental group. Okay, and if I consider a transverse section, okay, I will take the return maps. Okay, so I would like to give an example, a very simple example. So let us consider the foliation defined on a neighborhood of the origin of C2. Defined by the vector field x ddx plus lambda y ddy for some non-zero lambda. Okay, this is just a linear differential equation associated to this vector field. We can easily check that y equal to 0 is invariant by x, in fact, by the foliation associated to x. The origin is the unique singular point of the foliation or of the vector field. Okay, so if I take y equal to 0 minus the origin, we have, obviously intersecting with the set U, we have that this is a leaf of the foliation, and I will calculate the holonomy in this particular case. Okay, so if I take a contractible loop, obviously the germ will be the identity. So let me consider a non-trivial loop. So I have here the leaf. I have here the singular point. I will fix here a point epsilon. I will assume that epsilon is real, and I will consider a loop around the origin of starting at this point epsilon. Okay, and I will consider here a transverse section to the leaf through this point. Okay, so I can assume that this transverse section is constituted by points y epsilon y such that modulus of y is less than an arbitrary small delta, so that it is totally contained on U. Okay. So this loop, I can parameterize it as epsilon a to p I k 0. And if we take y sufficiently close to the origin, okay, I can take the lift of this path, and I will want to see to which point I will return on sigma. Okay, so to take the lift here, I know that if I take this lift in x, I will have exactly the same expression. Here I will have y of k, and y of k satisfy di dk is di dx, dx dk. So this corresponds to di is lambda, lambda y. Here the x is x, so epsilon a to p I k. We'll take the derivative of x, so it is 2pi epsilon a to p I k. So all of this cancels, and we get a linear differential equation on y. So this is very easy to solve. And so we know that y at k is the initial point here, y0, okay, times the exponential. Sorry, I forgot. Here, lambda. Okay. So it is the exponential of 2 pi I lambda times k. Okay, so if I want to look to this lift, I have to take the forced return map. So I have that the germ associated to this path gamma is just the map that, that to which each y I will associate a to p I lambda I. Okay? So I'll have just to take k equal to 1 to return to the same initial point on the loop, gamma. Okay, I'm not representing here sigma 0. Okay? As I said, I'm going to the group of germs of diffeomorphisms leaving P0 invariant. In fact, it could happen that if I take this transverse section, when I'm trying to do the lift, I can go away of sigma. Okay, so this map is defined not in the entire sigma, but at least in a disk centered at the origin. Okay, so domain of definition need not coincide with all of sigma. Okay, I can take the other maps. It's just to take more loops, and I have my group of holonomy. And every element may have different domains of the definition because of that remark that I make. Okay, so this is an example. I could mention here, for example, if lambda is an entire number, then obviously I have that this element coincides with the identity. Okay, so the holonomy is trivial. In the case that this lambda is rational, I have that this element here is periodic. And then we can consider the other cases, C minus Q. Okay, in this case, H is not periodic, but it can have different behaviors depending on if you are in R minus Q, or if you have a non-zero imaginary part. Okay, for example, if we are on R minus Q, Okay, it preserves the norm of y, but it is dense inside it, inside these disks. Okay, and otherwise, if I have a non-zero imaginary part, I can go far from the origin, or I can approach the origin depending on the sign of the element. Obviously, in terms of group, if I go in this direction and I'm going approaching the origin, if I go in the opposite direction, I'm going away. Okay, so essentially that's it. Okay, so this is an example, a very simple example. And now, the other part that I would like to talk is the holonomy of a foliation transverse to the fibers of a fiber bundle. That it is related to the talk of Frank yesterday. Okay? Okay, so if I'm looking to the holonomy of a leaf, I'm just going to the group of germs of diffeomorphisms of a certain transverse section. However, there are some examples, okay, where I can define the holonomy on a global transverse section, okay? So this is the case. So sometimes it is possible to define the holonomy of a foliation as an element of a diffuse of a global transverse section. Okay. And that, in fact, this global holonomy encodes the holonomy of every leaf of the foliation. Okay? And that encodes the holonomy of every leaf of the foliation. So this is the case of these foliations that are transverse to the fibers of a fiber bundle, and that I'm going to define. Okay? Okay, so to begin with, I'm going to define fiber bundle. Okay. So a differential fiber bundle is a four-tuple EF BP, where EF and B are manifolds. P goes from E to B, and this is a submersion. Okay, and satisfying the following condition. So for every point x on B that we fix, there must exist a U neighborhood of x on B okay? And there must exist also a diffeomorphism phi from pi minus 1 of u to u times f, such that the following diagram commutes. Okay, so I have here pi minus 1 being sent to u by pi. I have here phi going to u times f. And if I consider here p as the projection on the first element, so this has to commute. Okay. Alternatively, if we want, we can assume the existence of a covering of U of B. Okay, and elements phi from p minus 1 of y to ui times f, such that, again, the corresponding diagram commutes. So if I have pi minus 1 ui into ui by p, I have here phi to ui times f, and again, this commutes. So here, E is called the total space. Okay, F is called the typical fiber. B the base, and pi the projection.
Sorry, but we don't require that the PI is blue. They can just be random.
Sorry?
The PI, there's no condition on the PI. The PI is just happy.
Okay. Okay, so I'm going to define now what a foliation transverse to the fibers of a fibration of a fiber bundle is. Okay, so let me take EF BP, a fiber bundle. Let me take F, a regular foliation. I will say later the adaptation to a singular foliation. Okay, for instance, I consider a regular foliation. And so the foliation F is said to be transverse to the fibers of this foliation, of this fiber bundle. It's on E, on the total space. Okay? So it is said to be transverse to the fibers of the fiber bundle if the two following conditions are satisfied. So in the first condition, we ask the dimension of the total space to coincide with the dimension of the fibers plus the dimension of the foliation. Okay? And at the same time, for every point P that we fix on E, and if we consider, we denote by FP the fiber above P, or the fiber through P, to be more precise. And we consider by LP the leaf of the foliation also passing through P. Then the tangent space of E at P must be the direct sum of the tangent space at P of F with the tangent space of P of the leaf through P. Okay? So this is one of the conditions that needs to be satisfied. Maybe I can write still here. So the second condition that we ask is that for every leaf L of the foliation, if we take the restriction of P, the projection, to this leaf L, so the restriction of P to L yields a covering, a surjective covering map. Okay, so we are going from L to the base, and this is a surjective covering map. Okay, so 2 remarks on this. So the first remark is that the second condition is equivalent to say that PL has the path lifting property. Okay, so condition B is equivalent to say that PL has the path lifting property. I mean, if I consider a path, yes, I said regular in beginning, it's there. Okay? Okay, then I will say what happens in the singular case, okay? But for the moment, we are assuming regular. Okay, so here I mean that for every path that I consider in the basis B, and every point that I consider on E that projects on the initial point of this path on B, okay, there exists a path C tilde that projects on the initial path on the basis. Okay? Second remark is that condition A implies that the restriction of P to every leaf L is a local diffeomorphism. But it does not imply that it is a surjetive covering map. And to check if it is a surjetive covering map is a more subtle problem. Okay? Yeah, sure. So what I say is you have here your base B, okay? You have here your total space E. And if you consider here some path here on the basis, closed or not, okay? And if you consider a point on E that projects here, so it is on the fiber above this point, there must exist here a curve C tilde that P of C tilde coincides with C. Okay? This is important to the definition of the holonomy because you have to lift your paths that you consider on the P1 of your leaf or of your basis. Okay? To be sure that you can lift it is important. Okay, so as I said, condition A only implies that PL is a local diffeomorphism, and it does not necessarily ensure that, but there is one case where we know that this happens. So it is a result for Harassman that says the following: if the fiber F of our fibration, of our fiber bundle, is compact, then condition A implies condition B. Okay? And I'm going to make the proof of this proposition. Okay, so let us consider L, a leaf of the foliation, and let us take PL as a restriction of P to L. Okay? And to prove that condition B is satisfied, it is equivalent to prove that it has the path lifting property. Okay? So it is that we are going to prove. So to prove that PL is a covering map, a surjetive covering map, it suffices to check that it has the path lifting property. Okay, so let us start to consider a path on the basis. Okay, So let us fix a path on the basis. Let us fix a point P on E that projects on C0. Okay, and we want to check the existence of C tilde, a path C tilde on E, such that the projection of C tilde coincides with C. Okay, so I have here my basis B. I have here my path C. Okay. I have here my point C0. And I fix my point P here on A, on E, that projects here on C0. Okay? So I have my fiber. Okay? And we know from condition A, we want to prove that A implies B. We know that from condition A, that PL is a local diffeomorphism. Okay? So what does it say? It says that locally we can lift this path. Okay? So there is here a small path here that I know that projects here. Okay?
But in the path lifting, you are also requiring that the path starts at P, right?
Yeah.
It is not written, right? C tilde must be C tilde of 0 equal P, right?
Yes, yes, yes. Thanks. Thanks. Okay, so condition A implies, as I said, that PL is a local diffeom. So locally, C can be lifted. So let us assume for a contradiction that we don't have, in fact, a lift of all of this path C. So assume, aiming for a contradiction, that C cannot be lifted. Okay, so let T0 be the first element on 0, 1, such that C tilde, this local lifting, is well defined from 0 to T0 and not on T0, okay? And C tilde is not well defined on T0, okay? Okay. So I'm saying that I have here a certain t0. I have here my C of t0. I have the leaf, the fiber above it. Okay, I can lift C almost till this fiber, but I cannot extend to this fiber. Okay, so consider then this point CT0 on B, and let us fix V on the basis. A small neighborhood of this point CT0 with a trivialization coming from the definition of the fiber bundle. Okay, so V, the neighborhood of CT0, for which there is a trivialization coordinate coming from phi. Oh. Okay, so what happens now? We have our trivialization, so I have my V here. I have pi minus 1 of V. I have my phi here, going to V times the fiber, and making this diagram commute. Okay? And when I make T converge to T0, okay, by means of phi, we can assume, so I will say here that T belongs to T0 minus a certain delta till T0. Okay, so we can assume that C tilde of this set, of this interval, is totally contained in V times F. Okay, so instead of looking here, I'm going to look here. Okay, so I have that if I take the projection of C tilde of T and I take the limit as T goes to T0 minus, okay, so this is the limit of C of T, that is C at T0. So now the fiber F is compact. So this means that when I look to the C tilde here, or if I prefer to phi of C tilde, okay, this is going to a certain point, CT0, Q, where Q is in the fiber. Okay, so limit, sorry, there exists a sequence Tn going to T0 such that the limit of C tilde of Tn when n goes to infinity, this goes to CT0 Q, where Q is in the fiber. Okay? So up to reducing eventually this neighborhood V that we have considered nearby. No, I can't arrive there. So up to reducing this neighborhood V here, I can assume that I have a foliated coordinates there. Okay? So up to reducing V, we can find a foliated coordinate around this point CT0 key. Okay, so that in this foliated coordinate, we have the following. We have here V. Okay, we have here the curve in orange. I have here my CT0. I have the fiber. I have my point Q. And the foliation here is horizontal. Okay, but now if I look to phi tilde C tilde of T, okay, this is totally contained in a plaque here. And, okay, since we have here transversality, I have no choice then the all of CT goes to this point Q. Okay? So, in fact, C tilde of T, let me write, limit of all of C tilde T as T goes to T0 is Q. Yes, but because you have transversality. You have a subsequence that is going to this point. Okay? You are totally contained here. The fiber is totally transverse. So you have no chance then to go there. You are taking just the lift.
But the leaves are not straight. You draw straight, but like horizontal, but it doesn't need to be. It could be more irregular.
More?
Irregular. Like, I mean, the leaves don't need to be like.
I'm just considering our C infinity leaves or holomorphic. Okay, so okay. And it's proved. Okay, so this leads us to a contradiction. So in fact, we can lift everything. Okay. So this leads us to a contradiction. So C can be lifted. To C tilde, in fact, defined on all of interval 0, 1. Okay. Sorry? That V is? Well, if C is not connected, okay, if you have, for example, two different components, you are not going to connect one point from one component to the point. I have to assume that it is path connected.
But the condition P is equivalent to the lifting property you need connected, right?
Yes, eventually assuming that it is, I have just one connected component, but I can see this later and discuss with you. Okay. Yeah. Because when you think that you have the foliation, imagine that you have one-dimensional foliations. If you have higher dimensional, it is the same. You have just a unique lift passing through the point. You have just one unique solution. So the lift must have to be unique. Okay.
So it's just detail, but at the end to take a contradiction, you need to apply once more the fact that it's a local.
Sorry?
It's just a detail, but at the end to obtain a contradiction, you need to apply once more the fact that it's a local homomorphism.
Yeah, sure. Because here, okay, I have an extension to Q. As he's saying, here again I have a local diffeomorphisms, so I can extend a little bit more. Okay, so if I can put this here. Okay, so since PL is a local diffeom, we can extend the path C tilde in a certain T0 minus zeta tilde T0 plus zeta. And obviously, in the previous part, it must have to coincide. Okay.
There's not really, in this proof, the foliation condition is not really used, actually. You just need that L to be immersed sub-manifold that has the preciding condition.
Yes, we are essentially using this. Okay.
This kind of vibration, they have this lifting property independent of the foliation. Like covering maps, they have as well the back lifting property.
Yes, covering maps. Yeah.
In this case, they use the fact that the fiber is compact. I think.
For example, even if you take the universal covering, you take a path on M, and you can lift to your universal covering. Yeah.
Can compact can be changed with complete?
In any case, sorry?
Can compact can be changed with complete?
Can be?
Changed with complete?
No, which condition?
Compact.
And what do you mean by complete?
I mean, I have the limit of sequence, Cauchy sequence.
Yeah. Yes, I think so. Okay. Sorry, I didn't listen.
In this question of completeness, what would be the relation of the foliation and the metric?
The metric? Ah.
Completeness and Cauchy sequence is very metric.
Topology, I mean, you can say Cauchy sequence is just.
But here we are not using a metric. What is important to use here is that we have a subsequence that has a limit. Okay? But in any case, okay? So in this sense, the important part is that we have a sequences that have a limit. But in the other case, it does not ensure? No? Okay. Okay. Okay, so now we are sure here that if that we can take this sorry, I was lost when where I was. Okay, I'm here. Okay, so I'm going to see this here later. The application to the Riccati equation, as Frank has talked yesterday. I will view it very quickly. Okay, so with this, I'm going now to say the construction of the holonomy group of the foliation. Okay, viewed in fact as a group that is defined, the elements of diffu are defined on a global leaf. Okay, so let us take as our fibration. Again, let us still assume that half is a regular foliation. Okay, that it is transverse to the fibers of the fiber bundle. Okay, and let me fix a point P on the basis. Let me take a loop on the basis. And let me take F to be, or FP to be the fiber of P sitting over the point P, C0. Okay, so I'm assuming that my point P is the initial point of the loop. Okay, so for every point x that we fix on the fiber above x, we can associate an element that will denote in this way, that also belongs to the fiber. And we can associate it in the following way. So let us take C tilde, the lift of C in the leaf Lx that passes through the point x, okay, and such that c tilde 0 is x, okay. So the point that we associate, that I denote by ho c of p, is defined to be the final point of this lift. Okay, so I have this map, ho c s, from fp to fp, that to the point x associates the final point of this element. Okay, so this is a local diffeomorphism, but in fact it is a global diffeomorphism from fp to fp. So it is defined on all of leaf, okay? And it is global since, in fact, it admits an inverse that corresponds to the element associated to follow C in the opposite direction, okay? So I will put here C minus 1, where C minus 1 of t is C on 1 minus t. Okay? So it is in fact a global diffeomorphism. Okay, so we have then a representation. Sorry. Remark before that. It only depends, again, on the homotopy class of the loop C that we consider. As in the previous case of the holonomy of a leaf. Okay, and so we obtain, as I was going to say, a homomorphism or representation from the fundamental group of B at P now into the global diffeomorphisms of Fp, okay? And the image of Rho is said to be the holonomy of the foliation. I'm going to emphasize here. Okay, so definition, the image Rho of P1 of BP is called the global holonomy of the foliation. Okay, again, I have fixed here a point P. If I change the point, everything is isomorphic, so it is well defined. We can assume that we have a fixed P, there is no problem. Okay, as I said in the beginning, this global holonomy it contains, in a natural sense, the holonomy of every leaf of this foliation. Okay? So remark, the global holonomy contains, in a natural sense, the holonomy of every leaf L of the foliation.
Why did you call this point rho C of P and not rho C of X? To X you associate.
Yes, sorry. Thanks. Also, yeah, yes, thanks.
Thank you.
Okay, so how can we see this here? So let us fix L, a leaf of the foliation. Let us fix a point Q on this leaf. And let me fix a transverse section to L passing through Q. Okay, and as I said before, the holonomy of this leaf, okay, could be viewed as a representation from the fundamental group of the leaf at K on the germs, here it is in terms of germs, okay? It is not global, since we are in a leaf. We are just with a small section transverse to the leaf, okay? And, okay, I have the leaf here. I have the point Q here. I have an element, a path C that I consider here, and I have my transverse section passing through this point. Okay, so C is an element on P1 of the leaf at Q. Okay, H is an element of germs of the diffeomorphisms of sigma Q that leaves Q fixed. Okay. So HC is the image of C by that map. And one of the things that I can claim is that we can assume that H is not the identity, okay? Otherwise, the identity is the image of a contractible loop. So it is clearly contained in the global holonomy of the foliation. Okay, so we can assume that this is not the identity. In particular, the leaf L cannot be simply connected. Okay. Okay, so H is different from the identity implies automatically that the loop C is not contractible. Okay, and so the same for its projection. Okay. Okay. I said P, I can say P, it depends if I'm on A or in the fibration, okay? And this here immediately follows because P is a covering map. Okay. Now, we just need to see that to remark that it has a fixed point at the origin. Okay, so now it suffices to note that the image of this curve C bar, the lift, has a fixed point at Q. Well, but this is obvious because the curve C projects, is a loop, projects down, so C is exactly the lift of the curve that it is down, so we immediately have a fixed point. Okay, and the construction of the holonomy ensures that, in fact, nearby this point Q0, the holonomy here, the global holonomy, coincides with the other case. Okay, so the construction of the local implies that the local diffuse HC coincides with the rho of the curve C bar. Okay. So the global holonomy is defined in this case. So we started with a fiber bundle, a regular foliation transverse to this fiber bundle. We got a representation from the fundamental group of the bases into the global diffeomorphisms of the fibers, okay? But in fact, there is also a converse, and okay? So remark this construction of a global holonomy group associated with a foliation transverse to the fibers of a vibration admits a sort of converse and this is the proposition that we call the suspension of a representation. Okay, so proposition suspension of a representation and it says the following. Let us consider a representation of a fundamental group of a manifold B to the diffuse of a manifold F, okay? Where B and F are manifolds. Thus, there exists a fiber bundle EFBP with F and B considered before. And there exists also a foliation. So F on this manifold E that is transverse to the fibers of this fiber bundle. And such that the global holonomy group of the foliation is the image by Rho of P1 of B up to conjugation. Okay, so it is up to conjugation since if we consider two different points on the basis and we look to the representation, to the holonomy on it, on these different points, they are conjugated. Okay? So it depends on the point that we fix. Okay, so proof, not exactly proof because I'm not going to do all steps. There are some steps that I'm going to leave as an exercise. In any case, if you want, you can find all the details on the book of Camacho and Lins Neto. Geometric theory of foliations. Okay, so the idea let us consider P tilde universal covering of B. Okay, let us denote of B. Okay, we have sigma that corresponds to an action of the fundamental group of B on the universal cover by Dirac transformation. And now we are going to consider, sorry, the product of the universal cover by the manifold F we are considering there. Okay. Sorry. Yeah, I can say here sigma already, okay? So we'll consider this, and we'll consider also, in fact, I didn't want to say sigma here. I was going to use notation there, but I can use another notation, okay? So let us denote by tau the action of the fundamental group of B on, in fact, B tilde times F, okay? That is defined in the following way. Let us consider an element here of P1 of C, okay? Let us take X and Y. X is an element of P tilde, Y is an element of F. And the image will be the following. We'll take the action of C by X that I told there. And in the second component, so this is on B tilde, is the action by the sigma. And here on the fiber, what we'll do is the following. We just consider the image of the element I by the representation ρ of this element C. Okay? So this is in the fiber. Okay, so this action tau on B tilde times F is free, okay? Which means that if you take the image of C of a certain point xy, and this gives us xy, this means that the class of C is just the identity, okay? And it is properly discontinuous. Which means that for every point P, P1, P2 that we fix, there exists U, a neighborhood of this point, such that the image by C of U intersection with U is empty, okay? For every C that it is non-constructible, okay? And these conditions, they follow immediately by the conditions of the action of the deck transformation, okay? Okay, so these two remarks here implies that we can take the quotient of this product by sigma, by tau, sorry, and the quotient of this product by tau is a manifold. Okay, and this will correspond, in fact, to the total space of our fiber bundle. Okay, so the remainder of the proof is what I'm going to left as an exercise. Okay. So I'm going just to say what it has to be proved. So the remainder of the proof consists of the three verifications below. Okay, so the first verification that we have to make is the following. We can take a projection P tilde from the product B tilde times F on B that associates to every element B tilde F the projection of B tilde, okay, where this projection of B tilde is just the projection given by the universal covering. Okay? And this projection here is preserved by the action of tau. Okay? So this means that if we have two elements that are related through tau, they project exactly in the same element. Okay? So in fact, it induces a submersion on M from M to B. That is our projection map of the fiber bundle. Okay, so this is one of the things that needs to be checked. Let me just put here exercise. Secondly, the action of tau on B tilde times F also preserves the horizontal fibration on B tilde times F. So this means that it induces a foliation F on M that is also immediately transverse to the fibers of the fiber bundle, to the fibers F, I can say like this. This is very easy to check. Just remark the action that I have considered. Okay? If you look to the second component, the image of xy in the second component only depends on y. So if I try to make the change of coordinates, the change of coordinates in defining this, the horizontal foliation is going into the horizontal foliations. Okay, so I'm going to send y's into a function of y's. Okay. And finally, by following the preceding construction, we recover the holonomy group of P1 of B arising from this foliation here on M. Okay, we recovered that, it's missing here, that the holonomy of this arising from F to M is up to conjugation the initial representation Rho from P1 of B into the global diffuse of F. Okay, so last thing that I have planned to do on this was exactly to look to an application of the Hairsman result to the case of Riccati equations. Frank has already talked yesterday about this. In any case, I'm going just to make here to recall and to note that it can be viewed as an application of this. Okay? So application to Riccati equations. So the Riccati equation is a differential equation dy dx as ax y squared plus bx y plus cx, where a, b, and c are rational functions. Okay, we can always view it as an autonomous vector field. Okay, so view it as an autonomous vector field or differential equation. We can just say that I have dt, dx dt is 1, dy dt is a of x y squared plus b of x y plus c of x. Okay, but since a and b and c are rational functions, we will denote by p the least common multiple of the denominators of a, b, and c, and multiplying this by p, I have the following vector fields: px ddx plus, now I get a star of x y squared plus b star of x y plus c star of x ddy. And now P, A, B, and C are all polynomials. So I consider here the natural fibration. Whose projection I take? Sorry? Ah, star, yes, thanks. I take my coordinates x, y. I project on my first coordinate, x. Okay. And now, I will try to speak quickly because I'm in time. On this fibration, this vector field does not induce a regular foliation. Okay, on C2, it is not a regular foliation. Okay, however, if we denote by P1, let me write x1, xk on C, the roots of P, okay, we have that the fibers above x1, xk are invariant by the foliation, okay? We have that the singularities of the foliation associated to that vector field are contained in these fibers. Okay, and away from these fibers, F is transverse to the other fibers, okay? So, in fact, we can get a regular foliation transverse to the fibers of a fibration if to C2 we take off the union of these invariant fibers. So this can be viewed as an extension, okay, because I have defined for regular foliations. We can define this for the other cases. Okay, so here, this foliation A satisfies condition A. And what about condition B? So as Frank has said yesterday, what you should do is, okay, I have here C corresponding to the variable x. We have here the fibers that are C corresponding to the variable y, okay, and we should compactify this on C times CP1. Okay, so we compactify the fibers. Away from the infinity, we have transversality. So let me put here. So in orange, we have these invariant fibers that contains the singular points. On the other fibers, we have transversality of the foliation. Okay? We want to see that we have path lifting condition. Okay, so we compactify the fibers. We just have to be sure that in the infinity, we still have transversality with respect to these fibers. And this, Frank has made this yesterday. Okay, so Frank has checked yesterday that at infinity of the variable y, we still have transversality. Okay, so now the fibers are compact, so Ehrman ensures that condition B is satisfied. So every path on the basis can be lifted above. Okay? So this ensures that condition B is satisfied. And so we have, in fact, a representation of the fundamental group of C minus these k singular points on the basis onto the diffeomorphisms of our fiber that, in fact, as Frank has said yesterday, it is an element of PSEL to C. Okay, I have passed the time. Sorry.